We are taking the first question. State what is meant by internal energy of a system. The concept is there that internal energy is the sum of kinetic and potential energies of a system. So molecular level. So at a molecular level, there are two types of energies, kinetic and potential. So if you sum them, it is called, it is because it's a 2 mark question, it's a sum of kinetic and potential. So first you recall that for examiner, that U is equal to EP plus EK at molecular level. This is the first point. Second point, random distribution. It is a random distribution the atoms of an ideal gas occupy a container of volume this. The gas is heated at, achha, did you understand that concept R1, right? Because R is a constant. And when you compare two containers, R is the same for both. So when you equate them, the R will be not making any change. This is called the concept of constant. Constant can be ignored if a trial is repeated. An atom of an ideal gas occupy a container of volume this, at pressure this, and temperature is this. This is temperature. This is volume. This is the way we always try to convince the examiner in the actual exam also. Here it connected. The gas is heated at constant pressure. The gas is heated at constant pressure so that its volume becomes this. For the fixed mass of gas, it's like a heating process at constant pressure. When pressure is constant, it looks like a Charles law case. And but the gas is heated. He said the volume, the mass of the gas, amount of substance in mole. So here we can use the chemistry formula. Number of mole is equal to mass upon molar mass if the mass is given. Otherwise, ideal gas equation. He says for the fixed mass of the gas, calculate the amount of substance in mole. So what should I put for pressure? Oh, sorry. So I have pressure. What should I put for volume for a fixed mass of the gas?
Will we use 2.30 times 10 to the power minus 3?
The initial volume.
Yeah. And it's already in meter cubes, so same value.
Okay, 2.3 10 power minus 3. And the temperature is 180.
Kelvin, yeah.
So we can solve this and get the value.
It's 0.39. So 0.4 can be right?
We can make it 0.40. How many sig fig he has given us? He has given us 3.8. So he's running 3 sig fig.
Yeah. So 0.400.
The temperature in Kelvin. Now, what is asking the amount of substance, the fixed mass, the temperature is already given. So what temperature is asking? So is he asking the new number of moles? Sorry, new temperature, I mean.
Yeah, the T which is missing.
So we can use Stark's law. So we have used Charles' law.
-2.97 times 10 to the power -4.
10 power -4.
Yeah.
That's strange. How temperature can be in such a number? -4. It doesn't look
Yeah.
like. Can you check again? Because 10 power -3 will cancel out.
Wait 1 second, I'll try again.
Because logically, this such a number is not possible.
Okay, if I remove the 10 power -3, then I'm getting 297.
10 power -3 will be cancelled because it's the same thing in everyone, both entries. During the change in B, the thermal energy supplied to the gas is 980 joule. This is the energy supplied. Determine the work done on the gas during this change. Explain your working. This is law of thermodynamics. So do you remember the first law of thermodynamics? Delta W, delta U.
Delta W is equal to delta U plus V.
That is a formula. That's law of thermodynamics. Delta Q is equal to delta U plus delta W. It's a very important law. And we don't have internal energy. What is the formula for work done by a gas at constant pressure? Work done by
Do we do pressure times change in volume?
yes. So delta W is P delta. So we can use this formula, and we need to find the work done. Energy is given although, but it's not working here because we don't have the internal energy. Internal energy he is asking in the next part. So what is the pressure which was constant?
2.60 times 10 to the power 5.
So 2 point. And we have 2.3 and 3.8. So we can show the working.
So don't we do for volume 2.3 minus 3.8? Because change in volume will be from initial to final, right?
The final minus initial. That's right. It should be always final minus initial.
Then 390 joules.
How much is coming?
Negative 390.
Determine the change delta U in internal energy of the gas. Now, this formula needs a lot of discussion in normal classes because this is the general form, and this formula actually shuffles according to the case that it is work is done by the gas, work is done on the gas. So here, during the change, the thermal energy supplied. So as thermal energy is supplied, delta Q is positive. Delta Q should be positive. And what about the work done? Work done is already coming negative. So we are willing to find this. We should remember why we are keeping delta Q in positive, because heat energy is supplied. 980.
So 980 minus 390. 590.
Now, check this question. Oh, I have done this. Oh, sorry. Look at this question, June 21st. Look at the question in your book. By reference to the first law of thermodynamics, state and explain the change, if any, in the internal energy. Internal energy consists of two things, EP plus EK. Potential energy depends upon intermolecular forces and EK is a function of temperature. Now the formula is there. The lump of solid lead as it melts at constant temperature. Look at the temperature is constant. As temperature is constant, delta EK is equal to 0. Melting means separation will increase. Melting means molecular separation will increase. So we have mentioned this. So molecular separation increases. So if molecular separation is increasing, can you guess what will happen to EP? Internal EP. EP will,
EP will also increase.
potential energy will increase. And by reference to the first law, delta Q is equal to delta U plus delta W. It's a solid. When solids melts, a little work is done externally, unlike liquids or gases which do a lot of work. So this portion will be 0. So we have established the link, and heat is supplied because you're melting. Delta Q is positive. So delta U is positive, and it means it is an increase. So we have mentioned all the points here which are required to explain this one. Some gas in a toy balloon, when the balloon bursts and no thermal energy enter or leave the system, it means delta Q is equal to 0. When a balloon bursts out, do you think the gas is doing some work?
Yeah, the gas will do some work against the atmosphere.
Yes. So this is the formula, and balloon burst. So when balloon burst, volume increases, molecules work against the system. Delta Q is 0. Now we have to see about the equation. Delta W is 0. Oh, sorry, delta Q is 0. So delta Q is 0. Delta U plus work done. Now what should I do? Work is done by the system. Volume increases, work done increases. Now I have to find delta U. He is asking actually for internal energy. So internal energy will be equal to minus delta W. Now in these questions, always, which I tell my student that in maths and sorry, in physics, you can use maths in such questions, or you can use logic. Logic in physics is very strong and it can never make a problem. Maths being a basic algebra based function, so it can give a problem, it can give a mistake. When you are not providing any energy, how system is doing energy or work, how the system is doing, it means when you are applying force outside and your balloon is busting, it means the system must be using its own energy. The system own energy is delta U. So it means when you are not supplying any energy from outside, the system is consuming its own energy, delta U. So as a result, delta U decreases. It is just like the case when we store energy in our body by food, and we use that, we transfer that energy, our energy reservoir decreases. Among the three topics, ideal gas, temperature, and thermal properties of material is very important, and majority time it is there in part or full. Now you have to look for this question first.
Found, sir.
state what is meant by the internal energy of a system. We had a definition for it. It is the sum of a random distribution of kinetic and potential energies associated with the molecules of a system. By reference to intermolecular forces, explain why the change in internal energy of an ideal gas is equal to the change in total energy of its molecule. What was the concept? In an ideal gas, we assume that it has no intermolecular forces, which means internal potential is zero. This is a theory. This is a famous assumption. Now, if this is the assumption, then U is equal to EK plus EP. EP is equal to 0. So U is equal to EK. State and explain the change, if any, in the internal energy of a solid metal ball as it falls under gravity in a vacuum. Vacuum means no vacuum means no air resistance. So the ball is falling under gravity. It is there. And obviously, when there is no resistance, acceleration will be equal to small g. This question requires a very important concept to understand, that internal energy is not a concern with the kinetic and potential energies at a macroscopic level. We know that when something falls down, its potential energy decreases. But this is not that potential energy which internal energy is addressing. Internal energy addresses a potential energy which is associated with the molecular separation. So that's a very important concept of this chapter, that internal energy is not related with the macroscopic level changes, like when the ball is falling, its potential energy, gravitational potential energy decreases. But this is not a concern for this. Remember that U is equal to EP plus EK. And both of these energies are on in internal level. So if they are on internal level, we have to see the kinetic energy. A student can think that when something is falling down, kinetic energy will increase, but this is not internal. This is not the velocity. When you drive your car faster, the molecules in the petrol, the fuel of the car, are not actually accelerating. But if you heat it up, then it will increase. That is why remember this very important concept. At internal level, potential energy depends upon intermolecular separation, and kinetic energy depends upon temperature. So now you have to
So there is no change in internal energy for this.
this is a case that molecular level.
Yeah.
At molecular level, there is no change in intermolecular separation and no change in temperature. So delta EP is equal to 0. Delta EK is equal to 0. So delta U no change. Now let's try this question. This is November 19, paper 42. And question number 3. First, look for this question if you can get it in your book.
No, sir, it's not there.
Not there.
Yeah.
November 1942, 3. Actually, it's a very loaded question. And
I'll open it in some device. 1 second.
should I forward you the paper or you have it?
No, I'll open it on Google.
Okay, okay, just open it and start it. I'm just coming. Start this question. I'm just coming.
Okay, sir. It's the amount of energy, thermal energy needed per unit mass to change state.
It is the energy needed per unit mass to change the state, and he's saying specific, so mass is specific. A student uses the apparatus illustrated in the figure to determine a value for the specific latent heat of fusion of ice. The balance reading measure the mass of the beaker and the melted ice water in the beaker. Melted ice, beaker, and a rheostat. The heater is switched on and pieces of ice at 0 degree, are added continuously to the funnel so that the heater is always surrounded by ice. When water drips out of the funnel at a constant rate, the balance reading is noted at 2-minute interval. After 10 minutes, the current in the heater is increased and the balance readings are taken for a further 12 minutes. The variation with time of the balance reading is shown. The reading of the ammeter and of the voltmeter are shown from 0 till 10 and after 10 minutes. Ammeter reading and voltmeter reading. From time 0 to time 10, 65 gram of ice is melted. Use figure 3.2 to determine the mass of ice melted from time 12 minutes to time 22 minutes. So is he subtracting the values
Yeah.
from the case that from the time 12 to time 22? If we read 12,
It's 145 for 12.
145.
Yeah, 145 for 12 minutes. And for 22, it's 285.
So for 12 minutes, it is 145.
Yeah.
Okay. So for if we read from this point,
285.
then we subtract it 285 and 145.
140.
Explain why, although the power of the heater is changed, the rate at which thermal energy is transferred from the surrounding to the ice is constant. Now, is it a case of thermal transfer, thermal equilibrium, or something like that?
Is it because like there is no overall temperature change between like the
Because
surrounding?
we are adding ice. That one.
Yeah. Yeah.
So we are adding ice continuously. No change in temperature difference. Specific latent heat. Is it Q is equal to ml?
Yes, sir. But I think, wait, there was one more formula. 1 second.
Main formula is Q is equal to ml.
Yeah, but we can use the VIT is equal to ML because,
That's a heat transfer electrically.
yeah.
So we can use that. Determine a value for, so we are supplying electricity, so we can say that VIT is equal to ml, electrical heating. Make L the subject. Now, what mass we should take, 65 gram or 140 gram? We should see the data given us here. From 0 till 10, I have the data. From after 10, I have the data.
We'll take 140.
Huh?
We'll take 140.
If we take 140, then we have to take the second row in this table.
Yeah. 10 minutes. After 10 minutes, yeah.
But we can take any row.
Yeah, because the difference is 10 minutes only.
So voltage is 15.1. Current is 3.6. How much the voltage? 15 point.
1.
And how much time is there? It's 10. So should I make 10 into 60?
I'm not sure about that.
10 is minute, na? In physics, we convert time into second.
Yeah, okay, okay.
Then find the value of L. How much mass should I put? If I'm taking
140.
set of value 140.
Yeah. I'm getting 232.9.
Sorry. 230.
232.9.
230.29.
No, no, 232.9.
Calculate the rate at which thermal energy is transferred from the surrounding to ice. Rate is always something changing with respect to time. So the rate at which thermal energy is transferred from the surrounding to the ice. So the heater is providing heat from heater plus from surrounding. So these two are added. This is the total input heat.